Good day, everyone. So we are about to start our tinyML talks. Thank you very much for your participation and your attendance. So we are going to have a tinyML talk by Dr. Adeel Pasha. He's in Lahore University of Management Sciences, and the talk title is an FPGA-based accelerator for fast convolution layers in convolutional neural network. Before we proceed, we will just like to thank our sponsors. So our strategic partners are On Devices, ARM, Deep Light, Edge Impulse, Emza Visual Sense, Green Waves, Gravity Inc., HotG, Imagimob, Kilka Tech, Latent AI, Maximum Integrated, now Analog Devices, Micro AI, NXP Semiconductor, Profis, Qualcomm, Oxio, Reality AI, Renesas, Rexon Technology, SAP, Seed, SensiML, ST Microelectronic, Stream Analyze, SynSense, Sentient. Also, you can get information about the additional sponsors from Olga at the mentioned email. So we are going to have a tinyML Summit 2022, which is going to be in person from March 28 to 30, 2022 in Hyatt Regency San Francisco Airport. You can get the information about the event from the below link. Also, the registration is going to be open soon. Additionally, the best product of the year and the best innovation of the year awards are open for nominations between November 15th and February 28th. Also, the tinyML Research Symposium 2022 will be on March 28, 2022. You can get further information from the following link, and you can get the information about the sponsors from the sponsors at tinyml.org. So tinyML community is growing up. So we have our regular meetups. So the overall members is above 7.7K, having 43 groups in 33 countries. So that's something, a great sign. The community is moving forward. Along with that, the community is growing on the LinkedIn platform too. So there are 2.5K members having 4.3K followers. So it's highly recommended you also form your own groups, combining multiple people working in a same country so that you can contribute to the tinyML society. Yeah. So also all the videos, the previous video and today's video also for the presentation are going to be available on the tinyML YouTube channel. So you can subscribe to the tinyML YouTube channel for the updates and the notification. And also you can access all the prior videos, and also the today's video will be available later on. Moreover, regarding the next tinyML talk, it's going to be on Tuesday, February 1st by Dr. Muhammad Shafiq from the New York University, Abu Dhabi, UAE. So the title of his talk is Energy Efficient and Security for tinyML and Energy across a layer approach. So the webcast will start at 8 a.m. Pacific time. So you can contact talks at tinyML for if you are interested in presenting your work. Yeah. So I would like to introduce our speaker today. So Muhammad Adeel Pasha is a senior member IEEE, received his bachelor's degree in electrical engineering from the University of Engineering and Technology, UET Lahore, Pakistan in 2004, and MS and PhD degrees in electrical and computer engineering with specialization in embedded systems from University of Nice, Sophia Antipolis, Nice, and University of Rennes, France in 2007 and 2010 respectively. He is currently working as an associate professor with the Department of Electrical Engineering, Lahore University of Management Sciences, LUMS, Pakistan. He's also the Director of Electronics and Embedded System Labs at LUMS since 2014. He has several years of research and development experience and has published numerous referred papers in major international journals and conferences. His research interests include energy-efficient hardware design for compute-intensive applications, real-time scheduling for multi-core systems, and future platforms for green computing. Now I would like to invite Dr. Adeel to present his work, and then we can have a Q&A session.
Thank you very much, Dr. Wes, and a very warm welcome to the participants of the talk. So today I'm going to talk about one of the research works that was done by one of my previous student, Afzal. So Afzal is nowadays completing his PhD at HKUST, so Hong Kong University of Science and Technology. So so this work is basically already published in ACM transactions on embedded computing systems with the same name. So FFConv, an FPGA-based accelerator for fast convolution layers in convolutional neural network, or CNNs. So if you need more information about or a detailed information about the work that we did in so I will briefly cover it in the talk, but if you need further information, you can always go and read this paper, and you will get further insights. So before I move on with the presentation, so I would very quickly like to introduce LUMS. So LUMS stands for Lahore University of Management Sciences. So it's a small size private university situated in Lahore, Pakistan. So for the people who don't know Pakistan or Lahore, so it's a not-for-profit university which has a very with lush green campus, as you can see. So this is an aerial shot of LUMS campus. So we have so it started as a management university, as the name suggests, Lahore University of Management Sciences only. So this is right on the on the top right corner here. You have the School for Business Studies, so SDSB, Sulaiman for School of Business. But then it expanded into other disciplines, so including sciences and engineering, law, education, and social sciences. So there are all these different buildings. They are housing different schools at LUMS campus. And along with that, we have a lot of green areas and student hostels, as you can see in the picture. So now, after this very brief introduction to LUMS, so I will formally start the talk. Okay, so this is the outline that I'm going to follow during the talk. So I will start with a brief motivation and that why this work is important. Then we will move on to the further details. So we will go through different types of convolutions that can take place in a convolution neural network. So it can either be spatial convolution or a fast convolution. That is the the major crux of today's talk. And it will be followed by design space exploration that we did in this work for optimization of different parameters like filter sizes or the quantization that we performed in the work. After that, it would lead to basically the hardware that we proposed for this accelerator. And I will then conclude the talk with some quantitative and qualitative results, that how does our work basically compare to the state of the art. Okay, so convolutional neural networks are basically the one of the major categories of deep neural networks, or DNNs. So you can find different applications for CNNs. For example, you can use them in object detection, you can use them in object classification as well. So where you can classify the object in an image, you can go for semantic segmentation. This is necessary for scene recognition, and that all of these three major classification and object image processing problems then can find their application in numerous applications, modern applications like autonomous driving, where semantic segmentation can basically help an autonomous vehicle to treat the path. So what is a drivable region or what is not, for example, or to detect pedestrians, for example, and so on. Similarly, you can find the application in machine vision, or and in edge computing, or industrial automation as well. But the major problem with CNNs or any deep neural network is that it basically has high computational requirements. So which then effectively leads to very high power consumption or energy requirements. So we basically did a small sort of analysis or survey of different modern uh, uh, CNN networks, for example, LXNet or VGG or YOLO, so which is you only look once. So it's a CNN based neural network as well. So YOLO V2 as well. So as you can see that so there are different implementations either on you can see that either on FPGA like this U, which is the Zinc FPGA board basically, or ARIA 10, which is an Intel FPGA. Or you can see that there are GPUs as well. So Titan X is there, and then there is this embedded GPU, which is quite in fashion nowadays. So Jetson Nano basically. So you can see that you can find a stark trade-off between the FPGA and the GPU implementation. So you can see that the GPUs can give you very high throughput. So you can see that it can give you a throughput in the range of 6,000 or 7,000 gigaops. Whereas on the other hand, if you go for the embedded applications, so tinyML, what we are talking about, so Jetson Nano, for example, so you can get a pretty low throughput, so about 51 gigaops only. And that translates to frame rate of only, you can see that 1.48 frame per second for an image. So which is quite low, and which cannot be used in in modern image applications or some machine vision or computer vision applications. On the other hand, if you look at this last column, so which is an FPGA based implementation, so you can see that for the same network, they are able to achieve relatively higher throughputs, which is about 40 FPS. And that all translates into a very decent energy efficiency or a power efficiency, so gigaops per second, so which is throughput per watt. So in 1 watt, how much throughput are you getting? So you can see that an FPGA based design, it's getting a higher throughput per watt as compared to, for example, an embedded GPU, because it was able to achieve a very low throughput. On the other hand, if you look at the high-end GPU, so they are giving you a very high throughput, but they are also consuming a huge amount of power. So 227 watts, for example, for a Titan X GPU. So you cannot, of course, put that GPU in an embedded application, in an autonomous vehicle, for example, or in a mobile phone. So you have to find a trade-off basically between the computational efficiency as well as the power consumption requirements for the underlying network. So that basically motivated us to do or to pursue this work, and so we wanted to improve the performance while achieving a higher throughput as well. So we were trying to achieve a higher throughput, much higher than that was achieved already by, for example, this reference, but with a greater power efficiency. Okay, so moving on. So how did we achieve that? So basically, so if you look at the convolution, so CNNs, so convolutional layers basically, comprise of more than 90% of the total computation budget. So if you look at any CNN, so be it VGG or LXNet or ShuffleNet or MobileNets or any other network, modern network inception, so you can see that the convolution layers, they account for major computations. So more than 90% of your computational requirements, they are used in convolution layers. Then there could be some dense layers, and then there could be some batch norm functions and other stuff. But majority of the horsepower actually goes to convolution. So what we did in this work is to basically we tried to reduce the computational requirements for convolution layers using Vinograd minimal filtering algorithms. Vinograd is a mathematical basically function. So that was introduced way back in 1980s, but it found its major use case after the widespread of deep neural networks or CNNs. So basically, so Vinograd proposed a method to basically do efficient convolution operations. So and the convolution operations that were based on Vinograd's filtering algorithm then used to call fast convolution algorithms or fast con. So basically what they do, I will explain it in a moment. So what they do basically, they alter the algebraic framework for the convolution layers, and what they do, they reduce the number of multiplications, and instead of that, they do some sort of transformation, and that transformations are basically much less costly in computation. So both in terms of energy and resource usage as compared to the convolution, the multiplication operations. So just to give you a very brief comparison between traditional or conventional convolution and fast convolution. So this is a typical spatial convolution, or a conventional convolution. So that is implemented with the help of multiply and accumulate, MAC, or multiplication and add, we call it MULAD operations. So basically each convolution. So for example, if you want to convolve this input feature map D with this filter map G, so basically what you do you do a two-dimensional or three-dimensional convolution, and that convolutional basically results in an output map Y. So for example, this is a very quick animation to show how does this operation works basically in a spatial convolution. So you see, you take the filter map and you put it over your input map, and you then perform sliding window operation. So each mapping basically, so each of these operations, they result in a MULAD operation, and this results in an output tile, and that moves on. So it's a sliding window operation. So you can see that you get the next value and the next, so the next and the next. Okay, so and it goes on like that, and you basically calculate one tile, or one map, output map basically. So if just to give you one quick example, so if you want to compute a two-dimensional or 2D conv for a map size of 4, and output future output tile size of 4 versus and a filter tile size of 3, so 4 cross 3, and since we are using 2D convolution, so it would be M cross M and R cross R, so 4 cross 4 and 3 cross 3. So in spatial conv, in this sliding window operation mode, so you need to have mathematically speaking R square into M square multiplication, so 144 multiplication, for example. On the other hand, if I go for FastConv, so what FastConv does basically, it converts your your feature map and your filter map into different other matrices. So it takes your input feature map and it performs the data transform and converts it into a different matrix, for example U. And likewise, it takes the filter map or the kernel map G, and it again performs the filter transform on top of it and produces another matrix which is V. And then the beauty of FastConv or Vinograd minimal filtering algorithm is that both U and V matrices are of the same dimensions. So you can just perform an element-wise multiplication or EWM on top of it, and eventually you will get a matrix M. And then you perform an inverse transform on it, and you will get your output map. So again, so start with the input feature map, you perform a transform on it, and you get another matrix, which is U. Likewise, you take the the same input filter map G, you perform a filter transform, and you get a matrix V, and you can see that the dimension of both U and V matrices, they are the same. So you then do simple element-wise multiplication, which is much faster than your convolutional multiplications using that sliding window thing, and eventually you get this matrix M, and you perform an inverse transform on it, and you get the output matrix, which is Y. And if you do this in this fashion, so you are able to reduce the number of multiplications. So the one that you did in that sliding window thing were resulting in 144 multiplications, and here, since you are just doing element-wise multiplication, so you are getting only 36. So you see, your So from this try example, you can see that your overall multiplications are reduced by a factor of 4. But I mean, there are always trade-offs. So the additional compute that you're going to perform are in the form of these additional stages. So you have to convert this input feature map D into a U. So using data transform or likewise filter transform or inverse transforms. So what are these additional stages? So because these are the additional costs that FastCon incur basically. It saves you multiplication, but it does something else. So what it does basically, it does this thing. So if you look at this D transpose matrix, so this was defined by Vinograd for different sizes of M, which is your output feature size. So you can see that for an output tile size of 4, for example, so M4, this was the matrix that Vinograd proposed basically. And you can very quickly see that these operations, they are very simple operations compared to a multiplication operation. For example, this is simple, discarding the bits at that particular position. So if you're multiplying with 0, I mean you're just ignoring the data. Similarly, multiplication by 4 is just shifting left by 2 times. So you can see that this multiplication can be very easily implemented with a simple shift operation, or for example, shift and add operation. You shift by 2 times to your left and then add the same value again, so you get a multiplication by 5. So you see that. So this is the strength reduction that we're talking about. That so you are reducing the number of multiplications, but you are adding some shift and add operations. So since shift and add operations are much less compute intensive compared to a multiplication, so we are overall gaining in terms of latencies, in terms of power consumption, and in terms of total. So similarly, filter transform, if you look at it, so this is the filter transform, again can be implemented very easily using arithmetic operations, and this is the inverse filter transform stage. So it can also be implemented. You can see that either you are multiplying by 1 or -1, so you're just negating and so on. So this is how FastCon basically give the better performance than a traditional spatial convolution. So using this concept, then we started to explore that what should be a reasonable size for M, for example. So filter size optimization, because Vinograd proposed different matrices for different values for M. So what could be a good value for M, for example? In this try example, I'm showing you M is equal to 4. So there could be M equal to 2, M equal to 3, and so on. So we started off with a very quick design space exploration that what could be a good value for M. Because the number of multiplications in FastCon algorithm, they basically decrease quadratically with M. So if we are choosing a bigger and bigger M, so you can see that your multiplication complexity, it keeps on decreasing. So this blue bar here, you can see that. So this is spatial conv. So for example, you require 2 giga ops or 2 giga multiplications, for example. On the other hand, if you are using F23, for example, so where M is 2 and R is 3, so R is filter size. So filter size is constant, equal to 3. So you can see that you require about 1 giga ops. Whereas if you choose a bigger and bigger size, you are reducing the number of multiplications required to do the job. But on the other hand, since the larger the value of M you will choose, the larger would be the matrix, those transform metrics that I've shown you in the previous slide. So your arithmetic operations, those shift and add operations, they continue to increase with the increase in the filter size, the output size rather, M. So you can see that you have to find a trade-off. So on one hand, you're with the increasing M, your number of multiplications decrease, but on the other, you see they start to then saturate at some point. And on the other hand, your arithmetic operations, they just keep on increasing. So what we did basically, so we tried to then find a sweet spot, that what could be the sort of an optimal point yeah, or more efficient point where we can basically design our system. So for example, you can see that by increasing again m, so you can see that your number of multiplications, they are decreasing. But now, the difference between this graph and the graph here is that, so here I'm just showing you percentage savings, so from the previous design. So for example, so you can see that moving from F33 to F43, so there is a percentage saving of only 5%. Whereas if you go from 4.3 to 5.3, for example, so there is a percentage increase in the savings of 31%. But you can see that, so you see this is more costly than compared to, for example, this approach. So doing this design space exploration, what we did basically was to choose this value, so which was resulting in a sweet in a spot where you are getting enough complexity reduction in multiplication, but so there was a little increase, so there was a 25% increase in here, and then 5% here, only 30% increase in the arithmetic complexity. Beyond this point, you can see there is a delta of straight away 31%. So 30% plus 31%, it would lead to 60%. So we chose this one. We chose the filter size of 4.3. So m is equal to 4 and r is equal to 3 to design our system. Okay, so that was about the Vinograd algorithm that we're going to implement in our design. And on top of that, so if we look at the if the software implementations of these designs, so all of these algorithms, either you use TensorFlow or you use MATLAB, so they are implemented in floating point implementation. So single float 32 or float 64. So double precision or single precision implementations. But as you know that when we go to FPGAs, so if we use floating point implementations, so they become quite slow, because then you have to use DSPs, and since we don't have enough DSPs in our system, so you have a huge amount of mulad operations, so your design becomes basically a bottleneck. So in the second part of design space exploration in this work, we basically went for data quantization. So again, data quantization is not a new concept. If you talk about convolutional CNNs, for example, or conventional CNNs rather. So people have explored in depth basically different quantization widths. For example, even they have even gone to binarized neural networks, even BNNs. But the point is, till the point that we did this work, nobody actually explored quantization in fast convolutional algorithms. So all the fast convolutional implementations that we found were basically in floating point implementations. So even we did a basic design prior to this work that was published in date 2019. So that was also in a floating point implementation. So in this work, we decided then to go and do quantization. So explore quantization and see how does quantization affect the classification accuracies, for example. For that, we use ImageNet 2012 as a benchmark, and we then found top 1 and top 5 accuracies for different approaches. So we did 2 types of quantizations then. So we quantized the kernel weights or the filter weights, and we also quantized our feature maps, so which are either your input image or the output of previous layers. So we quantize them all. So as we all know that normally the filters or the kernel weights, they are centered around 0. So you get that very beautiful shape curve around 0 with a very low standard deviation. So since they are centered around 0, so what we did was basically, so it can go to -1 or +1. So we only reserve 1 bit in the integer portion, because that was enough. And we dedicated all remaining bits to the fractional part to get the maximum precision. So for example, if you're using a 32-bit fixed point implementation, so we will be using Q1 point or 1.31 for example. And so starting from there, we basically then did that how far we can reduce this the value for this psi, for example. So how can we, how how small this number could be. So we started with, for example, 17 bits, and then we went to 16 bits, then 15. So as we reach this 13, so you can see that our different designs, for example, VGG 16 or LXNet or ShuffleNet, they start to lose accuracy. So you can see that percentage loss in top one classification accuracy, they start to appear here. So for example, with 13 bits, I'm getting 6% loss, so 94% accuracy in top one. If I go to 12 bits, so you can see there is this drastic increase, so it goes to 44%. And if I go to say 11 bits, so the loss then becomes 99%. So I'm totally gone. I'm totally gone with ShuffleNet, for example. Or for VGG, it's 97% drop, so only 3% accurate. So by doing this, design space exploration, what we came up with, so we found that if we choose the value of 15 for the fractional bits, a total of 16-bit, fixed point data type, so we are getting a sweet spot where we are getting only negligible, reductions in top one accuracies, only 0.27% for VGG, for example, 0.29 for LXNet, and 0.41 for ShuffleNet, compared to a 32-bit floating point implementation. So similarly, we did a similar study for feature maps, or the input image maps, and we found that there the integer portion basically is the deciding factor. So if we have enough bits in our fixed point representation, that can carry our integer portion without overflowing, or without without overflowing. If we simply discard all the fractional bits even, so we will have very minimal loss in accuracy. So for example, this graph shows this thing. So if I am using only 0 bit in the fractional portion, so I'm using 12 dot, for example, 0, then you can see that I am having only negligible drops, for example, only 0.17 rather, or 0.024% for VGG, or 0.1% for ShuffleNet. So this this graph is sort of it could be eluding, because if you look at the y-axis, it's pretty small. It's going only from 0 to 0.14. On the other hand, this graph, on the other slide, was 0 to 100. So if I transform this graph to the same axis as well, so you can see that there is hardly any drop in accuracy. You see, so that's why this is what we chose. So we basically dropped all the fractional bits. So we went for Q12.0. So 12 bits for the integer portion, because that were enough to carry all the all the data in our feature map inputs, and no fractional bit, and that resulted in a very negligible loss in accuracy. Okay. So you see that we can go with a 16-bit fixed point implementation for kernel map, and only 12-bit fixed point implementation for for feature map, or for the feature map images. And if I give you a comparison or a trade-off, so with this negligible drop, only 0.024%, we are getting a 2.7 times reduction in hardware cost, because we will need 2.67 times less number of bits if you use this representation rather than a single precision floating point implementation. So this is the saving that we will be we are expecting to get in the end. So so after doing these design space explorations, or finding our to minimize our or optimize our filter size, and then reduce our data lengths to to appropriate sizes, we then move on to actual hardware design, the hardware design, very long. So yeah, so we basically went for a modular design. So where we designed a basic or a base convolutional engine, so which will be performing one convolution, for example, or and then that could be repeated. This could be instantiated multiple times. Given the available resources on an FPGA, for example, and you can duplicate it or replicate it enough number of times. Given the FPGA at hand. So our base CE convolution engine, it contains these 4 parts. So this is the overall picture of that convolution engine or CE. So here, this first part is data transform stage, which is right here on top left. So it's implemented in the form of a 3-stage pipeline. So you can see that there are 3 stages. One stage that converts, input floating point number to fixed point numbers in our, desired format. Then, for that transform, so we have to perform 2 multiplications. So B transpose D into B again. So you see, so there are 2 matrix multiplications. So what we did, basically, we could do it in 1 cycle, but that was resulting in a very long critical path. So our design was getting very slow. So we did pipelining there, and we went for a 2-stage here for a better throughput, for a reduction in latency. Similarly, we did filter transform because your filter has to be transformed as well to so this would give you a V, a U matrix. This would give you a V. Remember the primer I just gave you. And once you have these 2, then you can go for those EWMs or element wise multiplications. So 6 cross 6. So this is here, and this we implemented using the hard blocks or the DSP blocks on the Xilinx FPGA, for example. You can use Intel FPGA as well. So this was done using DSPs just to gain so the DSPs were there, so we used them to accelerate the hardware. And then finally, the last stage is then inverse transform. We have to transform this 6 cross 6 back to 4 cross 4 to reach the normal output tile size. So that was implemented in the form of this. You can see again, because there were 2 matrix multiplications, so we did it in 2 stages. Again, using the same logic that I just gave you with for data and filter transform stage. So overall, all these operations, you can see that, so both of them are done in parallel. So they would take 3 clock cycles. This one would take 1 clock cycle, and then this would take 2 clock cycles again. So about 6 clock cycles to do the whole job, but you are doing it in parallel. And once your pipeline is full, you can do the same operations in 1 clock cycle. So again, very quick, reminder to computer architectures. So once your pipeline is full, you are achieving, you're getting CPI of basically one cycles per operation or per instruction. Okay, but while we were doing this, since we transform and we change the dimensions of the matrix. For example, this filter which is of dimension 3 cross 3, it gets converted into a filter of 6 cross 6. So you see, it basically increases our memory requirements. So another important part in this work was how can we basically optimize the memory reuse. So because this is a very legitimate problem when we talk about FPGA-based implementations. Not all your feature maps or even your weights can come inside your FPGA or in your DRAMs. So effectively, you have to go to your DRAMs, DDRs, for example, and you have to fetch data at some point in time. So how to optimize that? So for that, what we did was we looked in the literature and we found roofline models. So roofline models are basically theoretical tools that basically give you that give you an attainable bandwidth given your attainable throughput under the constraints of your memory bandwidths, for example. So this ramp here, for example, is basically your memory bandwidth. So for example, 12.8 gigabytes per second. So this comes from your FPGA at hand. So I'm using, for example, Xilinx Vertex 7 FPGA here with a DDR3 RAM. So that gives me the peak throughput of this thing. Okay. And this vertical bar here, so this vertical dotted bar, it basically it then can slide left to right. So if it slides to the right, it means that your system is not memory bound, it is more compute bound. And if it goes to your left, for example, so it means that you are more and more you're getting more and more memory bound. So in this particular diagram, you can see that I am giving you the roofline model for VGG16D. So where this is the theoretical top limit for fast convolutional network that I use in my design. So it's the maximum theoretical limit was 4435 gigaops per second. So you can see that it it approaches that Titan X implementation theoretically speaking. On the other hand, if you go for spatial conv, so this is its top, roof line. You can see that this thing, so it's only 1100 gigaops per second. And in this bit, in between these two, limits, is basically the playing field. So where we can place or how efficient we can design our hardware basically. So there are three different points you can see on this line. So a red dot, or a green dot, and a gray dot. So basically we implemented three different designs, so that I will just explain in a second. So to optimize the memory bandwidth, or to play with this memory bandwidth here at the ceiling, so what we did basically, we did two types of data reuse. So first we did kernel map reuse. So basically we call it like we used to call it weight stationary approach. So where we load the weight once, or the kernels once, and we try to fully utilize it for each possible feature map that comes into the picture, into the system. And once the complete usage is done, then we discard it and we load the next kernel map. So this is what we did in our approach. So we loaded every kernel tile and we reused it fully until for a given channel, until for the whole 16, so full batch. So 16 batch size was 16, so we did for whole 16 batches for the feature maps. And similarly, when we you should recall padding, for example. So same size padding or different size padding. So when we do those sliding window operations, so that some values are reused, for example. So this tile will be overlapping with, for example, this tile, and it will be overlapping with this tile, and so on. So what we did basically, we did that as well. So for this, for example, featured tile, so this particular tile, you can see that if I loaded this file, this tile, next time if I will be loading this tile here, so this one, for example, so this, so I will not be loading the complete tile. I will reuse some previous values. So these upper two rows and these left two columns, so we will reuse it. So we will cache it somewhere inside our accelerator. So we did it using registers, or the onboard on chip lookup tables, or flip-flops in FPGAs. And we only loaded, though, you see these partial, these highlighted areas. So only these values were read from the external memory. So this reduced the overall data flow from the external memory. So we reuse. So we try to maximally utilize the kernel maps, as well as partially utilize the feature maps. So that resulted in better memory usage. So these are basically these points that I'm highlighting. So here, this red dot was with kernel reuse. This green dot was with both kernel and feature map reuse, and plus plus quantization that I explained earlier. And then this gray thing here was basically with another another optimization that we did truncation at the end of these stages, for example. So when you multiply to, for example, 16-bit numbers, your output would be 32-bit. So, but we truncated it to only 16 bits again to keep we did not let it go on loose, for example. So that also resulted in in lots of savings, of course, at the cost of certain small degradation in the accuracy. So that was this gray dot here. So this was the throughput that we basically achieved with our design. So 3624 gigaops per second instead of a theoretical top limit of 4435. So that would not be achievable due to the pipelining and the memory loading that we have to do eventually in our design. And this is basically then the final architecture, or at the top level, at the top module level. So where each of these CEs basically is, is this design. So each of this CE is actually this design. And we, given the available resources on our Vertex 7 FPGA, we were able to instantiate 64 of these CEs. So we could load 64, filter maps in per channel in parallel, and then we can keep them loading, keep them loaded in the system, and we can traverse different feature maps for the whole batch before discarding a filter map and reuse and then load the next map. So as I mentioned that filter and data transform, they are done in parallel, whereas then we go for element wise multiplication and then eventually the inverse transform. And we were able to perform 64 tiles per clock cycle once the pipeline is full. So that was about the proposed hardware, and now I will move on to some of the results. So we basically went for two types of results. So I will show you two types of results. So one is basically a qualitative sort of comparison without dwelling more in the numbers. So for example, so all these different works, so 4, 5, 6, and 7. So 4 is basically one of my older work that I mentioned during the talk as well. So date 2019. So this is here. Whereas then there are some other works as well. So you can see that. So if you compare them, so we compared for 4 different parameters. So first of all, quantization. So you can see that none of the works in the FastConv community did quantization. So we were the first ones who did basically design space exploration and did the quantization. So limited means that they didn't explicitly tell us whether they were doing it or not, but most probably they won't be doing it because nobody else did it basically, and the results were similar basically to other implementations. So multipliers per DSP. So multiplier efficiency, for example, or DSP efficiency. So you can see that most of them, they are achieving an efficiency of 1 because you can perform 1 multiplication operation per DSP. But this work here, 7, is giving you an efficiency of 2. It means they can perform 2 DSP operations or 2 floating point operations per DSP because they are using an ARIA 10 FPGA. So in ARIA 10, you have DSPs that can perform 2 18 cross 18 18-bit multiplications in parallel. So this is what they did basically. Then so 3 of these works, they didn't do accuracy comparisons. Okay, this number 7 did and we did as well. And finally, we were the only one who did stage level optimization. So these optimization I just told you: data reuse, filter reuse, and EWM truncation and so on. So we did that as well. And now moving on to quantitative then comparison. So this table basically gives us a holistic comparison. So how many DSPs we are using? We are using a bigger Vertex 7 FPGA, so we are using more number of DSPs, okay, compared to, for example, 8, but we are comparable to 4 and 5, for example, here. But look at the power efficiency. So you can see that we are getting much better power efficiency compared to the previous works. So we are getting if we, in terms of power efficiency, we're getting from 1 times to 7 times. So 7 times more efficient in terms of power. Similarly, 10 times more efficient, in terms of lookup table utilization. 7 times, 6.5 times, DSP as well, and about 19 times. So high throughput implementation. Okay, so we are getting much higher throughput than some of the works. For VGG16, similarly for LXNet. So again, this is another, you can see, a contribution of this work, that none of these works, they basically did, only one of them actually did a comparison across different networks. Others just designed their, accelerator for a particular network, for example, either VGG16 or say AlexNet. But we did it across, three different networks: VGG16, AlexNet, and then ShuffleNet. So that is used in GoogleNet and in modern networks. Huh? So we got similar results in AlexNet as well. So we are getting a power efficiency of 26 times peak compared to the three works, 38 times efficiency in lookup table, 41 times in DSP, and 42 times in throughput. So these are better than even VGG. So these were the quantitative results. So we are getting much better power efficiency. We are getting much higher throughput compared to the others. So to conclude, so we basically designed a hardware accelerator for convolution layers in a convolutional neural network, and we used Vinograd minimal filtering algorithm or FastConv in our design. So we performed extensive design space exploration for finding the optimal filter size for Vinograd algorithms, as well as the optimal fixed point implementation. We then also explored the memory or compute trade-offs, which is a legitimate issue with FPGA-based designs. And using those informations, we basically optimized and then constrained our design to an FPGA platform of our choice. So we did it for Vertex 7, for example. But we can adapt, so our design is adaptable. We can adapt it to a different FPGA, for example, an Intel ARIA10 FPGA, or for example, a Zinc Ultra Scale FPGA, or even a low-end FPGA. So the only trade-off would be that you would be able to instantiate lesser number of CEs or convolution engines. So your throughput would be relatively, reduced, but of course, that would be at the cost of a lower power consumption if you're going for a lower FPGA or an edge FPGA, for example. But of course, you will be using it for applications that are, that have much less number of, compute requirements as well. So we basically deployed efficient data reuse schemes in our design, so weight spatially, for example, and so on. And we then benchmarked our design for three popular CNN architectures: VGG16, AlexNet, and ShuffleNet, and we achieved a considerable amount of savings in terms of all different parameters: throughput, power efficiency, DSP efficiency, and so on, compared to the existing state-of-the-art algorithms. Okay, so that's about it. So thank you very much for listening to the talk. Now I open the floor for question answers. So thank you very much. So I will be taking the questions now. So Dr.
Thank you very much. Yeah. Thank you very much, Dr. Adeel, for a very much nice and interesting talk. I would like all of you to do that poll, and meanwhile also write your Q&A in the chat. We have some already Q&A in the chat box, so in a rather Q&A session. So I will read it. So we have first question, basically, how are these transforms derived? Are they some sort of fast Fourier transform? I thought, because we know that convolutional operational is converted to multiplication operation when an FFT is applied.
Yes, so Balaji, yes, so yeah, Balaji, basically, this is not fast Fourier transform. That spatial convolution that I'm talking about, that sliding window approach, that is actually FFT. So Vinograd is a different type of transform. So like we did FFT or fast Fourier transform, so Vinograd is a different type of transform. So it's not FFT, it's a different transform. So spatial con that we talk about, those are actually FFTs. So this comparison is actually between FFT-based, conv implementation and a Vinograd filter-based, or transform-based implementation. Okay? So yeah, so it's different than FFT.
Right. Yeah, we have another question. How about memory requirements for transformation matrices, whether taking into consideration to have a fair comparison in FPGA?
So this is exactly what what I basically mentioned in my slides as well. That memory is of course a major concern, but you have to efficiently, design, your basically, what we call it shuttling as well. How much data you get in from your DDR, your external memory into your FPGA basically, and how long you can keep it in your FPGA, for example. So if you are able to manage it, definitely you would be able to maximize the put. But eventually you will hit somewhere. You will hit that bottom, that top bar that I've shown you on that roofline model. That somewhere you will hit that bottleneck. So yeah, beyond that bottleneck, within those constraints, you can maximize the throughput. I just shown you that for LXNet or for VGG, we were able to, theoretically speaking, achieve a speed, a throughput of 4,000, about 4,000 gigaops, which is on a Vertex 7 FPGA, which is comparable to a Titan X GPU. I mean, which is much more power, power hungry, or much more bigger device. Yeah.
Yeah. So we have another question from Balaji. For fixed point 1.15 type, how would you represent negative, positive? Did you reserve another bit for it, or was 2's complement used?
So we didn't do 2's complement, because I mean, these are just, these normally 2's complements are used when you do additions. So if you are doing just multiplication, for example, multiply by -1, so you don't need to do 2's complement. You can just do a negation basically. So we went for signed magnitude representation. So, and where there were additions involved, we went for 2's complement. So it depends basically.
Right. Another question is on the transforms also. Are these transformation matrices pre-computed? What about their transform? And also, could these matrices be fixed for all the scenarios?
So these transforms, so they are again proposed by Vinograd. So basically, so these are pre-computed. We already know that what would be what would be the transform, for example. If I go to the slides, if I go to that primer slide. Yeah, so for example, this particular transform matrix, so this is already, designed by, for example, Vinograd in his 1980s paper. So he has defined different transforms for different values for M, for example, output tile size. So you can take it from there. And they exist for only certain number of values. For example, they are available, for example, for M is equal to 2 to M equal to 7, for example. But since most of the modern, or the vision related, or embedded related, or rather edge related designs, since our tile sizes are small, so we hardly go for a tile size greater than 4, I guess. So there could be Inception or I3D or other, but on the larger data sizes, so you can have layers up to 7 cross 7. But for hardly for any edge computing application, I can imagine anything beyond 3 or 4. So I think we can easily deal with that. That's why I used that particular size in my designs.
Right. We have another question. Was the DSP block part of the FPGA, or was it separate module that was integrated with Xilinx FPGA?
No, it's built-in modules on Xilinx FPGAs. So we use the IP cores for that, basically, for that DSP block instantiation.
Right. And also, was there a separate logic for ensuring data reuse apart from the local buffers?
No, of course, there would be an FSM, for scheduling the operations. So I've just shown you the data path, but there would of course be a control part that was controlling, that was scheduling these operations, that for how many clock cycles that particular, kernel tile would be there, or weight tile would be there. So of course there would be an FSM doing
Right.
that.
And also from the Vinograd transformation on the filter function, you have shown has divisions by 6 for F4 cross 4 or 3 cross 3. So not
Yes.
really sure you pass quickly. So how did you implement them efficiently? Do you use small dividers?
Again, so this is also an interesting fact. So in my previous work, that was that date paper. So we basically computed that offline, because these are these are weights. So weights are normally pre-computed during training. So you could basically, pre-compute, them and store them, and you can just, load it, pre-computed form. So we did that basically in our previous design, but we found out that that was actually creating a bottleneck, because then my memory bandwidth was increasing. So we computed it inside our FPGAs. No, we didn't use any special dividers here. So even though we could have done that, but we use simple divisions. So because these are division by integers, so we use simple, I mean, we coded it at behavioral level. So we just use the built-in operation, built-in function.
Yeah, and we have a last question. I can't find anything related to the data set used for the proposed architecture.
So a data set is ImageNet 2012. So it is a very common, highly cited data set that is used in all CV, computer vision related communities, CVPR. So yeah, so you can easily find ImageNet 2012. So you will even find a link to that data set in my paper. Huh? If you go to my paper, you can basically you can find the link. Huh? You can download it from there.
Yeah, thank you very much, Dr. Adeel. And also from the panelists, if participants, if you have any question, you can approach the tinyML forums and you can ask any question, and Dr. Adeel will be later on following up on those replies.
Sure,
Thank
yeah,
you
sure.
again. So we'll once again would like to thank our strategic partners. Also a little bit more detail about the executive strategic partners. We have ARM, the software and hardware foundation for tinyML. Edge Impulse, the leading edge ML platform. Qualcomm AI Research, advancing AI research to make efficient AI ubiquitous. Sentient, the neural decision processor and end-to-end deep learning solutions for tinyML and edge AI. But now the platinum strategic partners. DeepLight, we use AI to make other AI faster, smaller, and more power efficient. Tech, the global IoT solutions. Reality AI, the pre-built edge AI sensing modules plus tools to build your own reality AI solutions. Broad and scalable edge computing portfolio. The gold strategic partners. Maxim Integrated, the Maxim Integrated enables the edge intelligence. Latent AI, adaptive AI for the intelligent edge. Micro AI, and XP Semiconductors. Seed, the IoT hardware enabler. SensiML builds smart IoT sensor devices from the data. ST Microelectronics. SynSense builds sensing and interface hardware for ultra low power, embedded and mobile and edge devices. The silver strategic partners, Aeon Devices, EMSA, Grovity, Hotg, IMG, Oxo, Profis, SAP, and Stream Analyze. Also, just do remember the next talk, which is on Tuesday, February 1st by Dr. Muhammad Shafiq, New York University, Abu Dhabi. It's going to be at 8 a.m. Pacific time, and you can also contact talks at tinyml.org if you are interested in presenting your work. Last and the most important thing, the copyright notice that the multimedia file is copyright 2022 by tinyML Foundation. All rights are reserved. It may not be duplicated or distributed in any form without prior written approval. tinyML is a registered trademark for the tinyML Foundation. I will again like to thank all the participants and especially our speaker, Dr. Adeel Pasha, for his very nice and interesting talk.